In this video, we will briefly present our novel methods for Vertex-Blend attribute compression. Vertex-Blend attributes are used for skeleton-based animation and consist of an index tuple referencing a bone transformation and a weight tuple defining the amount of influence of each bone. Let's start with the index compression. When visualizing the index tuples of our test meshes by giving every unique index tuple a unique color, patches of equal color and therefore of equal index tuple appear. This is because vertices close to each other are usually transformed by the same bones. To utilize this coherence, we create a lookup table containing all the unique index tuples. The lookup table is therefore called the index tuple set. When compressing, first we fill this table with the index tuple of every patch. Next, we replace the original index tuple of every vertex with just a reference or an index to the lookup table. This table shows the effectiveness of this approach. In this row, we can see the originally required number of bits per vertex. As the number of bones differs between the meshes, the size of an index tuple differs as well. In this row, we can see that the bits per vertex required to reference a lookup table entry plus the size of the entries of that lookup table per vertex is smaller than the original size. We achieved compression. Let's continue with the weight compression. Vertex-Blend weights are non-negative and sum to 1. Therefore, we can calculate one weight from the others. When utilizing this, the resulting sample space for a 3-tuple of weights is a triangle. The same can also be applied to weight tuples of any dimension. The sample space of 4-tuple is a tetrahedron. The sample space for an n-tuple is the n-1 dimensional simplex. We can further shrink the original sample space by sorting a weight tuple. We must swap the corresponding indices accordingly. Sorting shrinks the sample space to an even smaller simplex. To simplify the sample space further, we shear or delta encode the weight values. To sample the triangle or tetrahedron, we create a sample grid. Only the sample points of the grid inside the sample space receive an index. This index is the value saved per vertex as a compressed weight tuple. For decompression, we need a way to find the I and j coordinate from the sample point index. We derive a function baseIndex. BaseIndex receives the grid size and the row index as an input and returns the sample point index in the first column of that row. For example, the BaseIndex of row 0 is 0, the BaseIndex of row 2 is 12, and so on. Next, we need to invert our baseIndex function to receive the j-index from a sample point index. After that, we know in what row the sample point lies and can compute the I-index. Now we can shear the simplex back to its original shape. We have successfully decompressed our weight tuple. We call this technique the optimal simplex sampling, or OSS. Thanks for watching.